All right. And so I understand, Jong, that your background is in topological phases, and you're a postdoc now at KITP. Is that right?
Yep.
And is it your first postdoc?
It's my first postdoc.
First postdoc, yeah. And where did you do your PhD?
At Harvard with Ashvin.
At Harvard with Ashman. There we are. Great. Yeah. So right. So it's a pleasure to have you here. Why don't you take it away?
All right. So I was initially trying to just reuse my slides from maybe a job talk, but I
That's
thought
fine.
I
This is
could,
like I know we're in Zoom and it's kind of more formal looking, but this is a
yeah,
group
but
meeting,
no,
so
no, but I
take
thought I
your
could probably be more specific now that I'm talking to a smaller group of people.
time.
So I intend to be a bit more technical than the general probably seminar type, because it's a smaller number of
That
people. And
works.
I also have a iPad right next to me. So whenever you have any technical questions, please don't hesitate. And so the talk talk consists of three parts. The first part, so it may sound irrelevant, but I'm gonna talk about measurement-based state preparation protocol. And then the second part, and then I'm gonna talk about the robustness of this measurement-based state preparation protocol. Like because like in this protocol, there can be there are three different ingredients basically. There's a unitary transformation part, and there's a measurement part, and there's a decoding part, and each of these ingredient can be perturbed kind of randomly. So I'm gonna talk whether this protocol has some kind of robustness against those kind of perturbations, and then I'm gonna finally talk about quantum phases under decoherence, like SPT or topological order under decoherence, and how decoherence can fundamentally induce some kind of information-theoretic transition. So as the title says, I'm going to talk about many-body physics of information. And yeah, I think this, I'll like start with a probably very kind of trivial examples so that like I intend everyone to follow. Right. So basically in this field of quantum information science and quantum many-body physics, the key ingredient is entanglement in large scale. So in quantum many-body physics, we all know that like entanglement in large scale can induce some exotic behavior, but it's also very important in quantum information science because this is what enables some kind of interesting quantum computations or fault-tolerant quantum memory. But before talking about this entanglement in large scale, it's quite instructive to think about classifying this entanglement based, and one criterion is basically a circuit complexity. What I mean is the following. So you can think about how much effort we need to create an entangled state starting from this trivial state, the trivial product state. And then if one only needs to apply the set of local unitary gates whose depth is finite as you're increasing the system size, it's called short-range entangled. But if you need to apply these gaps whose depth increases with the system size, then we call it long-range entangled. I personally think the name is not very good. It should rather be called shallow depths entangled versus probably like a deep depth entangled. But well, this is the way it's named by Xiaogang Wen, so I'll just follow how it's called. And this kind of classifications can be further refined by imposing a constraint. And the physical term for it is a symmetry. So if you only allow this entangled quantum state to be created using a symmetric local unitary gates, then things can be further, the classification can be further refined. And this really gives rise to a generic quantum phase of matter whose signatures can be associated with symmetry, thus more physical response. And there are lots of examples for this short and long range entangled states. Like the family of short range entangled states contain familiar kind of classical magnets, topological insulators, or superconductors. And long-range entangled states contain the cat state, or exotic spin liquid, and fractional quantum Hall insulators. And this kind of refined classification is also quite relevant in quantum information science, because when you have specific family of short-range entangled state equipped with a symmetry, this can be actually used to perform some universal quantum computation by performing a sequence of measurements. Also, when you have long-range entangled states, this can be utilized for some fault-tolerant quantum memory or topological quantum computations. So we can...
Quick question.
Yep.
So as an example of a long-range entangled state, a metal, like, can you create the ground state of a metal with a finite depth circuit, or do you need...
Right. So that's a good question. I think to create a metal, you need more than a finite depth, but actually, it's my guess is that it's not going to require you for the depth to be linear in the system size.
So it might be sublinear, but still grow system size.
Yeah. So
yeah, I think it is polynomial, because you have to construct this like fermionic Gaussian unitary, which has like polynomial depth.
I see.
So that's greater than linear when you say polynomial?
Yeah, it's, I think, yeah, I think it's greater than linear.
Greater than linear.
Oh,
interesting.
Yeah.
I see. Yeah, so actually here when I talked about short range and long range entangle, I guess I was kind of limiting myself to a gap state of base of matter. When it's a gapless, things are more complicated, and yeah. And also I have to remark that this kind of classification is not very rigorous. So yeah, I mean, but still, this kind of classification can be useful for some of the purposes,
though, right? Because you say, oh, you mean as long as you need to have extra assumptions, I suppose, because the you know, you're taking limits as n go to infinity, and you're making pretty sharp statements, right? It's finite depth or growing, and you know, it's kind of a I guess it's...
But yeah, so this is really a motivating slide, and I'm going to talk about the stability of entangled many-body states. Now, the entanglement is really important. It's also important to think about whether this entangled state is really robust under some perturbations. And before talking about that, I think it's useful to think about how we think about kind of state preparation. So there are basically two kind of mainstreams. And the first one is, you know, there's a usual condensed matter approach where you prepare a chunk of crystal, and then inside the crystal, electrons or spins interact with each other with natural Hamiltonian. And this Hamiltonian automatically gives rise to some energetic hierarchy among different entangled states. And when you just cool things down, if you consider the case where it's gapped, meaning that the lowest energy ground state manifold is separated from the other, at low enough temperature, you know that you're going to prepare the lowest energy state with not much additional kind of components. So this is really passive because you get to prepare what's dictated by the material's natural Hamiltonian. But, you know, with all this programmable quantum devices, you can actually create entangled state in a way you want. So roughly the idea is that you just initialize a circuit into a very well-known kind of product state I, and then you apply a sequence of gates to get some entangled quantum states. And if your gate implementation is faithful, then you're going to get what you want. But actually, in this active engineering of quantum state, this is only half the full story, because the non-unitary evolution becomes very important in this kind of active engineering. The fact that you can engineer individual qubits and unitary gates between them implies that you can also introduce some non-unitary perturbations at very UV scale. And this is very different from quantum materials, if you think about, because, okay, in quantum material like electronic state, it also couples to gapless phonons, or there's other perturbations, but those kind of coupling is actually often can be safely neglected because there's a difference in time scale or energy scale. But here you just get to inject this UV perturbation in a non-unitary way. So it's really important. And actually there are two types of non-unitary evolutions. The first one is a measurement and second one is a decoherence. So in this regard, we can think about two directions. The first one is whether we can do something more with measurement, because measurement is one of the key defining features of the quantum mechanics. If we add this measurement-induced kind of dynamics to a unitary quantum state evolution, it might be able to achieve something more interesting than just with unitary evolutions. And the second question one can ask is, under the presence of decoherence, which is the coupling of your quantum system with the environment, can we really trust our noisy quantum devices? Like you may claim that with your quantum device with certain decoherence level, you're saying that, oh, I can achieve certain tasks. Like Google said, oh, we achieve certain supremacy that classical computer cannot simulate. But if there's a certain noise level, that claim might not be true at all. So one really has to understand what they can do and not at the certain level of like noise or decoherence. So there are lots of like recent experimental efforts to really understand these ingredients. And in today's talk, I'm gonna talk about these two parts in rather intertwined manner. So in the first part, I'm gonna talk about this adaptive state preparation, where measurement is used as a key ingredient to prepare a quantum state. And the second part, I'm gonna talk about many-body entanglement in noisy quantum devices, which will actually provide a kind of fundamental understanding of what we can do under the presence of noise for this adaptive state preparation. Any questions so far? It's quite high level. And
Sounds
yeah,
good.
so in the first part, I'm going to talk about how we can combine these three ingredients, namely finite depth unitary gates, measurements, and feed-forward operation based on the measurement outcomes to implement a projection to a long-range entangled states in a very efficient manner. And then I'm going to talk about when each of these ingredients can be faulty, and then ask questions whether this projection to a long-range entangled states can be robust. So probably you all know basics, but let me just clarify. I'm gonna mainly talk about QB state in this computational basis 0 and 1, which is basically spin up and down, as you can see in this block sphere. And then when I say Pauli operator Z and X, it's just this. So Pauli X operator is going to exchange two states. And then I'm going to talk about mixed states a lot, which is a classical mixture of multiple pure states, each of which contribute with a probability pi. And to represent this mixed state, actually the quantity we have access is this density matrix, which is given as a pi, psi I, psi I. All right, so often we think about measurement as a way to extract information from quantum states. So, when this black box is preparing the same quantum state A0 plus B1 repeatedly, we can measure the state, and then the probability to obtain certain measurement outcome depends on this coefficient by Born rule. So by just keep measuring it, we just learn about the state. So measurement is really used as a way to kind of learn about the quantum state. But the fact that it collapsed the quantum state into one of the components in a measurement basis can allow us to use it as a tuning knob to manipulate quantum state. For example, let's say we have this entangled state in the gray area. And let's say we measure the standard side in X spaces. And there are two possible outcomes. So depending on the outcome, we get either red entangled state or blue entangled state. But let's say we know how to prepare the gray state, and what we want is this red state. So then like we can just prepare and measure and only select outcomes whenever the outcome is +1. So this is probably a very primitive way, but in this way, using measurement, we can prepare this red state potentially in a more efficient manner. But actually, measurement-assisted state preparation can be more interesting, and one of probably the most well-known example for this measurement-assisted state preparation is quantum teleportation. So here I'm gonna talk about a very simplified version of quantum teleportation, which demonstrates all the essential features of measurement-based state preparation. So here we prepare two qubits, A and B, where A is in this quantum state psi, and B is initialized in this simple state 0. So initially we have this simple product state, and now we're going to entangle two sites using this controlled X gates. This is a very simple 2-qubit unitary transformation. All it does is applying Pauli X operator based on the first qubit to the second qubit. So if the first qubit is 0, it doesn't do anything. But if the first qubit is 1, it's going to apply a Pauli X operator. So this is something very simple. If you have any questions or cannot understand, should ask. All right. So the 0, 0 will be mapped into 0, 0 under this 2-qubit unitary, but 1, 0 will be mapped into 1, 1 because the Pauli X operator is going to flip the second qubit from 0 to 1. So after this, you get this entangled state. And now, let's say you measure the first qubit in Z basis. And by looking at this, you can see that the probability of getting 0 or 1 is A squared or B squared. And whenever you get certain outcome on the first qubit, the state in quantum state in the second qubit just follows the outcome. And by repeating this experiment, you simply learn the state psi. So there's nothing interesting here. But you can now try to measure the first qubit in a Pauli X basis instead of Pauli Z basis. And for that, I rewrite the first qubit in a eigen basis of Pauli X operator, plus and minus. And once I rewrite in this way, you can see that probability of getting plus or minus is now really a 1/2, 50-50. Also, once you measure the first qubit, the quantum state in the second qubit will be actually A0 plus B1 or A0 minus B1, depending on the measurement outcome. So it almost looks like we teleported the state from A to B, except there can be a random phase modification. So, okay, we can teleport the quantum state if we only select the measurement outcome plus, but actually we can do better. If we actually apply Pauli Z operator based on the measurement outcome on the first qubit, we can deterministically get teleport psi from A to B in this way. So what we learn is that if you just combine entanglement and measurement, we get to stochastically steer the quantum dynamics of a entangled state. But when we combine entanglement, measurement, and decoding, post-measurement transformation based on the measurement outcome, we can actually deterministically evolve our quantum state. And
is this sort of like error correction?
Yeah, so error correction is also, if you think about it, it's really a measurement-assisted state preparation, right? Because you measure all the syndromes, and based on the syndrome measurement outcomes, you determine what transformation to perform or not. So anything that involves measurements and follow-up transformation can be fit into this framework. So I really like this example because this really demonstrates all the essential features of certain protocol that involves measurement. It can be error correction, measurement-based state preparation, and actually quantum teleportation is just one particular example of this measurement-assisted state preparation or state engineering, I would say. And if you think about, you can ask this question, okay, why is it possible to teleport your state when you measure in X basis, but not in Z basis? But if you think about when you measure in Z basis, you get to learn about the quantum state. This quantum state, entangled state, some information, A and B, but that information leaked out to the observer. But when I measure in X basis, probability is 50-50. You don't learn anything. So the information about A and B should remain within the system. And this is because our entire universe, the way it evolves, is unitary. Because our entire universe is evolving in a unitary way. If certain information leak out to the observer, that means, okay, you cannot do teleportation anymore. But if that information stays there, it must be there in a certain form. You may have to perform decoding transformation, but it's there. And this is actually the key ingredient for also measurement-assisted state preparation. When you're measuring it, you should try not to learn about the underlying state or underlying structure you want to kind of maintain. If you learn it, then that structure disappears. If you don't learn it, then that structure remains in a certain form, and that can be extracted based on how you decode, how you apply a transformation based on the measurement outcome. Okay. Any questions so far? This was probably
I have another question.
Sure.
So in this case, right? So A and B are sharing a bell pair.
Yeah.
But say that like you have you have a system that is evolving under like some more complicated unitary, right?
Yeah.
So can you perform teleportation with like, with systems where like which has been evolved under some like arbitrary unitary, which creates entanglement? Or do you need like some specific structure to be able to perform teleportation between like two parts of the system?
That's a great question. So as you can see, teleportation has not been achieved until we perform the decoding transformation, right?
Mm-hmm.
Because if you average them, because each of this A0 plus B1 and A0 minus B1 can appear 50-50. If you kind of average them as a density matrix, the resulting density matrix has kind of look like almost like a mixed state, like so. And when you use some very complicated unitary transformation, finding a proper decoding transformation based on the measurement outcome can be computationally very difficult.
I guess you also have to find the right measurement to do, because as you were saying, you might reveal information, so you don't want to do that.
Finding a proper teleportation protocol for arbitrary unitary scrambling transformation is very difficult. So it's but for some structured kind of unitary transformation, this kind of teleportation, finding a proper teleportation protocol should be possible.
But with some like,
it also has to do with the point that when you apply a generic unitary transformation, it's going to bring your state into a like a volume law state, with some highly entangled state. And in that kind of state, measurement outcomes almost look like the one without any structure. Those generated by some random number generator. And the remaining state also kind of looks like that. What it means is that when you have a kind of very complicated state, trying to come up with this kind of classical processing and decoding procedure can be probably practically not possible.
Yeah. I see. So what you're saying is like, if you have some arbitrary unitary, let's say that creates like volume law entanglement between two parts of the system, you can still perform teleportation from one end of the system to the other, but the decoding becomes like very complicated. But you can still do teleportation in theory.
Or teleportation would be only allowed for a very short window of time. You probably have heard of this Google wormhole experiment recently. That's not really a wormhole. It's really a quantum teleportation at many body level. And yeah, I mean, but in such a case,
I imagine if you had this big unitary and you do a measurement locally, because it has spread the information across the whole system, there's sort of a protection. You're not really going to measure much of the information, I guess.
Exactly.
So it does sound like you could do some kind of teleportation. It just might be hard to pull back out what that information is because it's now spread
Yes,
across.
yes.
Well,
I mean,
the one thing that's different about this channel specifically is that you go from the, like, once you create the bell pair and then you go and, you know, measure that, you have a fully quantum state to a fully classical state. But if you have a long range entanglement scheme and then you have a local measurement, then you're still keeping a significant amount of quantum information in that channel from input to output. So it's not going to be, so in order to extract any classical information from that, you're going to have to do something to the rest of the state in order to extract
yes.
the exact type of information that
Yeah.
we're doing here.
Yes.
Yeah.
Anyway, so that's the kind of main message. And let me now talk about how we are going to use this measurement assisted protocol to prepare a long range entangled state. And I'm going to use a cat state as an example. So if you want to create a cat state, the superposition of zeros and ones, or more generally, the superposition of two oppositely magnetized, macroscopically magnetized components, you have to apply a unitary gate whose depth increases with the system size. So if you just apply the sequence of controlled X operator, actually you can create the cat state. The problem is that controlled X gates do not commute with each other, so the depth really increases with the system size. You cannot just collapse them. You can also prepare them in a dynamical way. So if you think about transverse field Ising model, if your transverse field is very, very small, the ground state will actually be a cat state because it's a spontaneous symmetry breaking, but with small perturbation, the true ground state will always be a cat state, right? And if your transverse field is very, very strong, then you're going to get just a polarized simple product state. So using adiabatic evolution, what you can do is first start with a ground state is a plus product state with very, very large GT and slowly turn it off in such a way that you can adiabatically evolve this initial state into a cat state. But while doing so, you go through a phase transition, meaning that if you want this adiabatic preparation to be faithful, you should be slow enough, slower than this rate determined by this gap proportional to 1/L. So total evolution time to prepare the cat state in this way will also increase with the system size. So no matter what you do, if you want to prepare things in a unitary way, the total preparation time increase with the system size. And that's pretty bad if you think about quantum device. For example, in the superconducting qubits, the most of the loss or decoherence comes from the qubit lifetime. So longer the circuit is, more likely that circuit experience the decoherence. So basically you want to have things much faster. So as a theorist, you can imagine implementing some projection operator starting from this product state. Because this product state contains zeros and one components, in principle, if you can implement some projection operator, you'll immediately get the cat state. And this kind of projection operator, another way to think about is implementing an imaginary time evolution. So when beta goes to infinity, it's only going to leave the all zero and all one component. So you're going to get a cat state after this imaginary time evolution of the simple product state. But of course, this is imaginary. It is impossible to implement this in a real life. So the way we're going to take is kind of modularizing this into smaller pieces. So we're going to measure ZZ operator everywhere, starting from this product state. So if you start from this product state and measure ZZ everywhere and only select the +1 outcome, and this procedure is called a post-selection, only selecting the certain outcome you want, then by combining this measurement and post-selection, you can actually get the cat state. But there is a significant problem. First, measuring kind of multi-body operator in the quantum device can be quite non-trivial. And second, the thing is that when you measure in ZZ, the plus and minus appear with the 50-50, meaning that if you want the cat state, you actually, the chance of getting the cat state will decrease exponentially with the system size. It will be 1/2 to the n. So we want to avoid these issues. And I'm going to talk about how we can avoid these issues.
I see.
So
So
first-
far, you've basically just transferred the problem from one area to another, almost like you still have it's still, I mean, I don't know if linear in circuit depth is the same as exponential in number of measurements, but it's sort of sounds like a similarly difficult problem.
Yeah, but I'm gonna show that actually you can avoid this post-selection problem in this
Okay.
case. So first, let me talk about how we can do a multi-body measurement. So we're gonna introduce this Ensela qubit, the Y qubit, in such a way that when we entangle them and measure this white Ensela qubit in Pauli X spaces, depending on the measurement outcome, it actually gets to specify the correlation between ZZ, the red qubits. So in this sense, you introduce Ensela qubit and entangle such a way that this white qubit encodes the domain wall information for the red qubits. So the way it works is this. So you prepare all the red qubits and introduce Ensela qubits and apply this control Z gates. And this control Z gate will actually allow you to measure ZZ operator once you measure just a white qubit in Pauli X basis. The reason is the following. Let's say red qubit is 0 and these two red qubits are 0 and 0. Then control Z operator doesn't do anything, so you're gonna measure plus. If it's a 1, 1, it's gonna apply Pauli Z operator twice, so it will still be plus. But when it's a 1, 0 or 0, 1, then Pauli Z operator will be applied only once. So Z operator applied to plus will flip it from plus to minus. And then once you measure in X basis, you're going to get minus. So in this way, this measurement tells the domain wall configuration for the red qubits without kind of directly measuring the red. So if the measurement outcomes are all plus, then you're going to get cat state. But there still remains this post-selection issues. But by now, it must be clear because what I'm going to do is applying a certain transformation on the red qubits based on the measurement outcomes in this white qubits. If they are kind of domain wall configuration, we know exactly what red qubits are pointing opposite to a certain reference point. So if you can flip it back, then we're going to prepare the cat state. So it goes as this. So let's assign a spin up for the first qubit as a reference. This is a plus state, so it's a superposition of up and down.
Jong, I actually have a question.
Sure.
Could you explain really quickly why so you couldn't stack the X operators because of non-commutivity, but you can stack the Z operators in time? Yeah. Is that what I'm understanding? Could you explain why? Yeah,
because control Z operator is actually written as linear combinations of multi-qubit Pauli Z operators.
Oh, right. Okay.
They all commute, but
right.
control X operator involves X and Z.
Right.
Which does not commute with the neighboring one. So you cannot kind of pass one to the other in a control X case.
Perfect. Thank you so much.
Yeah. Another way to think about this is that to create a cat state, you have to entangle the leftmost qubit to the rightmost qubit. And if you just apply a sequence of unitary gates, I don't know whether you've heard of Lieb-Robinson bound, but when you apply a local unitary gates, there's a kind of limit on how fast entanglement can propagate. So, which means that if you want to entangle leftmost qubit and rightmost qubit, you just divide the distance by the Lieb-Robinson bound, then you need at least certain amount of time the time proportional to the system size to entangle the leftmost qubit and the rightmost qubit.
And has this bound been explored with like superconducting qubits and like the lifetimes of them? Like is there like so basically I guess my question is it possible for superconducting qubits to even reach this, or is the Lieb-Robinson bound going to is that a hard cutoff so that a superconducting qubit would decay before having a chance to get entangled? Has there been a study of that?
In what circumstance?
So like if you have so you said earlier that the superconducting qubits lifetimes are short enough where having this
it's large enough so that it's about like say a 10 microsecond and each gating time is about like a 20-30 nanoseconds.
Oh, okay.
So you can apply kind of hundreds of kind of gate depths in parallel, as long as they are kind of commuting with each other.
Sure.
So,
I
so
see.
you can apply about 100 kind of gates to entangle them. And if the
Okay.
100 gates is enough to entangle leftmost qubit and rightmost qubit, then you achieve the job. But if
Right.
your system size is very large, the 100 depth 100 might not be enough to entangle leftmost qubit and rightmost qubit, right?
Yeah. Thank you.
Okay. So right now I'm going to talk about how to avoid the post-selection. So if your measurement outcome is minus in the second qubit, the third qubit will point opposite to the first qubit. And if this is plus, the fifth qubit will point same direction as the third qubit, and so on. And then you should not forget that the first qubit was in a superposition of up and down. So after all the measurement, you're going to get superposition of two different components. So it's almost like a cat state, except it's not all up plus all down. But now you know which qubits to flip based on this measurement outcomes. It's really this third, fifth, and seventh qubit you have to flip to get the cat state you want. So indeed, after applying this spin flips, it's just a product of single spin flips. It's a very simple operation, just steps one circuit. And then you're going to get desired cat state, no matter what your measurement outcome is. So graphically, what this means is the following. So let's say this psi c as the state where your red qubits and white qubits are entangled. Then if all the measurement outcomes on your white ancilla qubits are +1, then you're going to get a cat state. But there's always a very large chance that you don't get the blue trajectory. So if you don't do anything, your experimental setup will just prepare this density matrix, the ensemble of all different pure states. It's psi s, which appears with this probability ps, like 1/2 to the n. And this will kind of look like a maximally mixed state, just thermal. But if you apply this single spin flip decoding transformation based on the measurement outcomes, you will actually map all different states into a cat state. So the density matrix you get will be actually a density matrix for pure cat state. So this box comes up again. If you combine entanglement, measurement, and decoding, you can actually evolve your quantum state in a deterministic fashion. So this decoding is really, really important. And another way to view this is that by combining these three ingredients, I effectively implemented this cat state projection operator or this imaginary time evolution operator, right? And this analogy will be actually pretty important in the second part of the talk. All right, so you can ask, are we done? But as I said, there are lots of perturbations in your quantum device. There can be a systematic bias on your quantum circuit. For example, your gate may over or under implement certain phase rotation. And also, there can be a random control failures, or it can couple to environment, or your measurement outcomes can be corrupted. So there can be also this UV scale non-unitary perturbations. So really, one have to talk about stability against these perturbations, because our quantum devices are never going to be perfect. So there are really three layers of questions. First, does each trajectory have a non-trivial correlation structure? As I showed, although only the first trajectory, the blue trajectory I showed in the previous slide had a cat state structure, all the other trajectory was also kind of like a cat state, has an interesting correlation structure already, right? But it's possible that most of the trajectory might not be even interesting at all. I mean, what I'm saying is that each of the trajectories is already long-range entangled. The decoding was necessary to convert this differently long-range entangled state into a single identifiable form. So the most important question, the 0th order question or first question you can ask is whether each trajectory is already interesting enough. Then we can talk about whether we can decode them into a single identifiable form. And then I can talk about whether I can generalize this framework into a broader class of quantum orders, like fractones or some subsystem symmetricals or something more. And I'm going to answer these questions using some intuitions from condensed matter physics.
So what you're saying is that the problem you studied might be a little too simple because you always had you had this nice structure for each of the possible outcomes, and then it was just a matter of one more layer of unitaries to fix. But the general problem will not be like that.
Yeah. Or when I say general, I mean general in the cat state.
Yeah.
Okay. All right. So for that, we have to kind of zoom out our perspective a little bit. I treated this white ancilla qubit as if they're kind of second-class citizen whose whole purpose is allowing us to perform a kind of two-body measurement, the ZZ operation on the red qubits. But together, they actually form a specific short-range entangled state with symmetry called a cluster state. And this cluster state is actually characterized by this correlation, the ZXZ being 1 for any 3 neighboring sites. So from this, it's actually quite clear that if you specify the middle X, the value of the X, you're going to immediately specify the ZZ correlation. And this is really a kind of SPT state, the short-range entangled state equipped with a symmetry, because the state is symmetric under 2 operations, namely a spin flip on the red qubits and spin flip on the white qubits. And this is actually characterized by a string order parameter or a non-local order parameter. So if you consider this operator, the Z, 2 Z's on the each end on the odd sides and product of X on the middle on the even sides, it's going to take a finite value no matter how long this string is. And from this, it's quite obvious that if you just measure all the X operator on the even sides, the white ancilla qubits, it will immediately specify all the ZZ correlations on the odd sides, red qubits. And it's going to be a long range correlated. Furthermore, while doing so, you're not doing anything. You're kind of still respecting the Ising symmetry on the odd sides. So it's going to be a superposition of kind of 2 different components, as you can see. Is it clear or?
Just to be sure, so the ZXZ, so that's the Z's are on, the X is on the ancilla, is that right? And the Z's
that's
are
what
on
I
the red
intended,
sides?
but actually this holds for
Or does it hold for any pair, any
3 neighboring sites.
It doesn't matter. So it could be ancilla qubit and a red, white, red, or white, red, white, doesn't matter.
Yeah.
Okay.
Because if you think about this situation, it's actually kind of symmetric, right? The situation is quite symmetric because control Z gates, although here I represent it as if as some direction, control Z gates is actually a symmetric gate. It's actually it's a Z1 plus Z2 minus Z1 times Z2 plus 1.
Okay.
So it's a totally symmetric gate. Yeah.
Okay.
All right. So now this actually implies that because this is a kind of quantum phase of matter, meaning that it's stable under perturbations as long as perturbations respect the symmetry. If you apply some random set of gates which respect this 2 set of Ising symmetries, then this non-local order parameter will be still finite. It will never vanish, meaning that after the measurements, let's say S is the label for the measurement outcomes on this ancilla qubits. Then the resulting state will still have some long-range correlation for the odd sites. But we can also think about the case where measurements itself can be faulty. For example, you may imagine the situation where measurements are kind of performed in a kind of slightly rotated basis, not exactly along the X, but maybe slightly rotated. And this can be effectively represented as having some unitary rotation right before the measurements. Or also, we can imagine a situation where measurement outcomes can be corrupted, which can be effectively captured by some decoherent channel. And in these 2 cases, what I can show is that we don't even have to go to a decoding stage. Already at the each quantum trajectory level, their ZZ correlation is just exponentially decaying. So each quantum trajectory is already trivial. And you can ask why. So what I showed in my paper is that if you consider this a post-measurement wave function for certain measurement outcomes, this post-measurement wave function is actually given as a wave function obtained by performing an imaginary time evolution by this finite time beta over 2, starting from this simple product state, where beta is given as a inverse tangent hyperbolic cosine theta. So when theta is 0, the beta is indeed infinite, right? But when theta is finite, when there's any finite rotation, beta is finite. And this Hamiltonian is actually given as some sort of Ising Hamiltonian with whose basically the coefficient sign depends on the measurement outcome. So when you have slight rotation, you're not implementing the desired projection operator. You're implementing some imperfect one. And the resulting wave function correlation structure will be actually governed by a classical StatMech problem of this 1D Ising model at finite temperature. And what we learned in undergrad StatMech or advanced StatMech is that 1D Ising model at finite temperature has no long-range correlation at any finite temperature. So it's only long-range correlated at 0 temperature when beta is infinite. And as soon as beta is finite, the order is gone.
What you're talking about here is a systematic error. Is that right?
No, here now, yeah, but actually, yeah, you're right. But this theta can be non-uniform.
It could be non-uniform, I see, but it's still systematic.
Yeah.
Right. So this sounds like actually a nice way. You could invert this problem and say, well, let's try to produce the best cat state. And if experimentalists could readjust, where they're doing how they're doing their measurements, they could optimize and figure out how to make it unbiased. Because exponential, we've got an exponential sensitivity here, it seems. So that might be a nice way to fix
to benchmark your device or
benchmark your device or even build the device.
Yep. So the faulty measurement outcomes can be also understood in a similar way. So here, what's happening is that with probability P, the measurement outcome, your readout doesn't give you a true measurement outcome. It's going to report you a kind of reversed measurement outcome. And that can be effectively captured by imagining a quantum channel which apply Pauli Z operator randomly with probability P right before the measurement, because Pauli Z operator is going to flip the eigenvalue of the Pauli X, right? And the problem is that here, after the measurement, what you're going to get is not going to be a pure state wave function anymore. It's going to be a mixed state, because when you observe certain measurement outcome S, it can be originated from various different measurement outcomes, each of which corrupted to be seen as what you see, right? So it's going to be a probabilistic mixture of various different pure states. The way to think about it is that, like when you observe a certain measurement outcome S, you may think, oh, it's coming from this specific trajectory. But each of the other trajectory can be corrupted to be look like this S. So there can be contributions of various different components. And when you add them up, what I can roughly show is that the post-measurement state is given as a mixed state, which is captured by roughly this thermal density matrix. At temperature beta, it's related to the probability P by this equation. So what it means is that when P is 0, when there's no error, beta is infinite, meaning there's a 0 temperature again. So it's just going to be a cat state. But when P is finite, beta is finite. And this is very similar to rotation if you relate theta and P in this way. So it seems like, oh, in 1D, we have no hope. Whenever there's a measurement error, we are not going to get a cat state. But we know that in 2D Ising model of finite temperature has a robustness, right? So probably we can imagine going for one higher dimension. Indeed, we can imagine red qubits at the vertices of the 2D lattice and introduce all the white ancilla qubits and then entangle them in such a way that the ZXZ is 1. And now if you just measure all the white ancilla qubits, it's going to give us all the consistent kind of domain wall configurations. So say we assign certain directions starting from the top left corner, and then we know whether the other red qubits are opposite to the top left or not, then we can perform decoding, as I mentioned in the previous slides. But now the problem is whether this white ancilla qubit is rotated or the measurement outcomes are faulty. And I mentioned that this can be effectively mapped into this imaginary time evolution. And then I can show that up to finite theta or up to finite error rate p, each quantum trajectory, most of them will still be non-trivial, will have a long-range correlation structure. And that threshold theta or p is pretty large. It's either 40 degree in terms of angle or about 11% in terms of error rate. Now we can ask the question about how can we perform decoding in this case? Any question?
I do, but I think you're going to answer it, so I'll let you continue.
Okay. So for the decoding perspective, I'm gonna specifically consider the faulty measurement case, but the other case also pretty similar. So when there's no error, measurement outcomes on the white ancilla qubits correspond to domain walls, which is a relative spin orientation between red qubits, so we can just decode. We know which spins to flip to get a cat state. But now, when there's some error, the domain wall configurations can be actually frustrated. What I mean is the following. Let's say white to be the measurement outcome plus and blue to be the measurement outcome minus. And let's say this is our measurement outcome. And this is actually frustrating. If you assign, say, spin up for this qubit, and then move, the top left should be also spin up. This one should be also spin up because the whites are all plus. This one should be also plus, so up. But now when you go from this to going back to the original place, because there is this blue measurement outcome, it says it should flip the sign. So when it goes back to itself, it changes orientation, meaning that something is wrong. There's no way to assign a relative spin orientation between red qubits that's consistent with the measurement outcomes. Actually, if you think about this white ancilla qubits are really a relative spin orientations, the product of them around any pocket must be a plus. So if the product of them is actually minus, that means something is wrong there. That means the probably certain measurement outcomes are kind of corrupted there, right? So under the presence of this frustrations, if you want to figure out kind of consistent relative spin orientation for the red qubits, now that's going to be a classical computational problem called Bayesian inference. For given corrupted measurement outcomes, you want to identify the relative spin orientations on these red qubits. So this is really a kind of classical computation problem. You have to infer what the correct kind of relative orientation is going to be for given corrupted outcomes. All right, so
can you explain why it's classical?
Oh, because
there's some superposition that comes up that's just, I don't know. It has
so
to
in this way, you're not going to get a pure cat state anymore. You're going to get an ensemble of kind of slight different cat states, whose total magnetization will be now kind of reduced, but they will all have the same phase coherence and similar kind of total magnetization. So although it's not going to be a pure cat state, it's going to be ensemble of coherent cat state, which has still like diverging Fisher information and so on. So yeah, you're right. It's not going to be a pure cat state anymore. It's going to be an ensemble of cat state. Because, yeah, so the way it works is the following. So you prepare the vertex and edge qubits in a plus basis, and then you entangle them. And then let's say you just rotate them or just corrupt them, and then measure in Pauli X basis. And now it's going to give you some patterns of frustrations I mentioned. And based on these patterns of frustrations, you run your classical computer to figure out underlying relative spin orientations for these vertex qubits. And so this is like some kind of inference problem where what you have is this kind of likelihood function. For given patterns of frustrations, you have some relative spin orientations assigned with certain probability. So this classical computer is going to sample the potential all different relative spin orientations. And after generating that, you pick the most likely kind of relative spin orientation, and based on that, you're performing a spin flips. And then you're going to generate a cat state ensemble satisfying these three conditions. First, it's going to have a vanishing magnetization, but it's going to have a non-trivial long-range correlation, the ZZ correlation. And also, it's going to have the phase coherence, meaning that if you just apply this Ising spin flip, it's coming back to itself without additional phase factor. And once you have an ensemble of cat states satisfying this property, it's in terms of quantum information processing or any kind of additional manipulation, you take advantage of the cat state. It is almost as good as just a pure cat state. So there's not much difference. And as I said, like things going to be exactly the same even if you just replace this to just the measurement error channel. All right, so
can you tell with the inference problem that you have some confidence in your choice?
Pardon?
The choice of state, like you do this inference problem.
Yeah.
To choose a set of the spin flips, right?
Right.
But it's a probabilistic
choice,
right?
Yeah.
So can you have confidence that you're doing the right spin flip?
Yeah, so that's what I'm going to talk about now.
Oh, okay.
So I mentioned that the first layer of question, there is this hard threshold where below at least each of the trajectory is mostly long-range correlated, long-range entangled. But above, trajectories are not long-range entangled, so you don't even dare to try decoding. So the question you can ask from the perspective of decoding is, can we actually saturate this cutoff? As long as each of the trajectory has a non-trivial long-range entanglement, can we always decode them into an identifiable form? So this is the so-called decoding phase diagram, where x-axis is a true error rate, true measurement error rate, and the y-axis is the error rate assumed by your decoder. Because this is a Bayesian inference solver, it has to assume what the underlying error rate is going to be. So along this red line, it is actually ideal decoder, meaning that the error rate it assumes is exactly the true underlying error rate. So along this red line, so if you look at this phase diagram, if you're in this red region, it means you can decode your state into have a long-range entangled structure. But beyond, it's not. And if you look at this threshold along this red line, it's exactly coinciding with the true threshold from the first layer question, meaning that there exists this ideal decoder such that it can decode as long as your quantum trajectories are non-trivial. But what it also established is that even if you have a non-ideal decoder, meaning that it assumes error rate different from the true error rate, like say this blue line, blue dot, it performs almost as good as the ideal decoder. I can actually show that this blue decoder can decode up to kind of 0.104. So only a 5% performance difference. And another benefit is that this blue decoder is really, really fast. This ideal decoder, this is a Bayesian inference solver, and it's basically a maximum likelihood kind of method, and that kind of maps into a classical Monte Carlo simulations, which can be pretty slow. But this ideal decoder is guaranteed to have a maximum complexity of polynomial kind of computational complexity, and it actually performs a lot faster than that. And using this non-ideal decoder, which is much faster, I kind of simulated the experiments, and this is the result. Here in the first plot, I show the squared magnetization because this is a cat state. Magnetization vanish everywhere. So I calculate the squared magnetization and normalized squared magnetization for different system size. And you can see that it indeed undergoes a phase transition around near the true transition point.
And you can see that because of the way it collapses. Oh, that's the second.
Yeah, if you look at this variance of this squared magnetization, it diverges at the critical point. Yeah. So what I establish here is a stability under non-ideal decoding protocol. So now this cat state has really the notion of stability because it can be stable under kind of this unitary transformation. Can be stable under measurement procedure. It can be stable under that decoding procedure. So it's in some sense like a new phase of matter. I mean, people nowadays talk about interactive phase of matter, where measurements and decoding is a part of the essential ingredients. And another way to think about is that when each of these ingredients deviate from the ideal protocol, it simply gives rise to a finite beta, right? And when this projection operator has some still non-trivial phase, then this protocol kind of conspired to give some stable phase of matter. But if it's not, then no. So also in some sense, you see that this kind of procedure is a lot like just a classical physics. Not much quantumness is there, at least in terms of kind of phase structure, because this protocol maps into just a classical step map problem. But anyway, we can generalize this framework to various different states. For 2D Tori code case, what I can show is that at any deviation from the ideal protocol, it actually maps to a finite temperature two-dimensional Ising-Gauge theory, which has no ordering. So this 2D Tori code preparation using measurement is not robust. If there's a measurement error or decoding error, it's immediately going to be disordered with some finite correlation length. And that correlation length is even kind of analytically solvable as a function of error rate. But the thing is that 3D Tori code preparation using the measurement is actually robust. And of course, 3D cat state preparation is also robust. And what's quite interesting is that 3D generalized cat state preparation is also robust, which is a superposition of exponentially many components. But what's kind of weird, or maybe not weird, what's kind of interesting is that 3D fraction state preparation using measurement is fragile. And that has a degeneracy of 2 to the 6L. So it's, I think, quite interesting that while this weird kind of highly degenerate state preparation is robust, fraction state preparation is fragile using the measurement assisted protocol. So that's
what is the fraction state?
All you have to remember is that fraction state is a three-dimensional kind of spin model whose degeneracy is a 2 to the 6L. So in the ideal case, when I run the protocol, I'm going to get some ground state, which is a superposition of 2 to the 6L different components. But that's fragile. As soon as kind of protocol slightly deviates from the ideal setting, it's going to just break apart. But in this case, this one is actually robust. And that's quite interesting in my opinion.
Is there some relation here between robustness and error correction? Like
there is. Actually,
so in other words, is there a notion of, in error correction, you've got this distance, a given code as a given distance. And if you allow for these errors,
well, code has a distance, but
when you think
about error correction, distance doesn't really matter.
the error correction code has a distance, right? Like it can, if you have, if you create an error with a weight, with a weight less than, I think it's half the distance, then you can always fix that error.
But
Whereas
that's about the single error. When you talk about error correction in general, you consider the case where system is under kind of just decoherence channel, noise channel, where it can apply kind of noise kind of everywhere with some probability. So when you talk about the quantum code and distance doesn't directly tell you about kind of error threshold, in fact.
So the distance I'm referring to is people usually give a few numbers when they define a code.
Yeah,
One of them
yeah, I agree.
one of which is the distance,
Yeah.
right?
Yeah.
And I guess what's really nice about topological codes is the distance grows with the system size, so you get a really robust code out of that.
Yeah.
So I guess so what I was wondering is your measure of your study of all these different errors and perturbations, do you find cases where or maybe like each of these states has a sort of similar notion of distance, where if you to introduce errors of a certain rough level, errors that are a certain level of power, they could destroy their chances of building that state. Like you mainly gave like sort of local single qubit kind of errors, right? But what if you had 2 qubit errors or 3 qubit errors? And
yeah. So actually, I'm going to talk about that in the next slide.
Okay.
Yeah. So here you can see that this boundary is also in some sense kind of error threshold, right? Right, to prepare the qubit state. And also for each of this kind of state, they also have some error threshold respectively. Yeah. And I'm gonna uncover that in more detail. Let me use just 15 more minutes.
15 minutes? I don't know if I have 15 minutes. I'm gonna have to go soon.
Okay. So what
I could leave and you could keep talking. We could do that. If anybody else is willing to stay, is that possible? So I'll have to leave in about 3 minutes or so, I think.
Okay.
But is everybody else willing to stay so we could hear this? Or am I the only one that has to leave?
I can record.
You can keep recording. You can stay.
Yep.
Okay. Let me just.
Why don't you continue with your 15 minutes, and I will watch the video or something afterwards.
Okay.
Maybe I can send you more.
What I said can be rephrased as extracting long-range entangled state from the noisy short-range entangled state using measurements and decoding, right? So it's like a short-range entangled state is like a resource, and this resource kind of disappears beyond certain error threshold. In the previous case, it was when the measurement error was above 11%, right? Yeah. So now you can ask this question: what is the noise threshold for a state to be a resource, or even verifiable, in a sense that when you have this 2D cluster state, the fact that you can extract long-range entangled cat state out of this 2D short-range entangled state is also a way to verify that you actually prepare the 2D cluster state, right? So actually, if you cannot prepare this long-range entangled state, that means you don't have a 2D cluster state. So also, in some sense, there's a noise threshold for the state to be verifiable. You have a certain quantum state, and if the measurement error rate is beyond certain value, then you cannot even verify whether you prepared the interesting state or not. So I basically developed a new framework to understand this entanglement structure of the mixed state as the following. So motivation is this. People often talk about non-local order parameter as a reason why we can get the long-range entangled state, because once you have this non-local order parameter, if you measure all the x in the middle, you get long-range correlation. But once you have a local dephasing error, this correlation actually decays exponentially with the length. So it cannot be the reason why we can still extract a cat state from the 2D cluster state, as I showed in the previous slide. Because like what it shows is that for any finite error rate, your non-local order parameter just decays exponentially. But I show that, okay, it doesn't matter. We can still do this until a certain threshold. So there should be something else. And I'm going to what's behind of all this. So I named it as a conditional correlation or strange correlation in a more technical term. So it's defined as the following. Let's say you measure all these Ancela qubits and measurement outcome is S. Then condition on this measurement outcome, you can get the correlation function between the remaining red qubits. So as long as the remaining red qubits are long-range correlated, still you can extract the cat state out of this, right? And you don't care about the sign. What you care is whether there's some long-range correlation or not. So what you really care is a weighted average of the absolute value of this conditional correlation for all different measurement outcomes. If this quantity is still long-range correlated, then you can still extract a cat state even if there is a decoherence. But if this is trivial, there's no way you can extract a cat state from this. So once you have this conditional correlation function, decoding would correspond to finding a proper kind of flip transformation to cancel a sign of this conditional correlation. Because the conditional correlation can have a random kind of sign structure. And if you want a cat state, what you want to do is canceling them by just flipping the red qubits. Also, what I showed in my paper is that this previously considered criterion, a non-local order parameter, is actually given as a signed summation of this conditional correlation function as this, which is upper bounded by what I showed earlier. So even if each of the CS is a long-range correlated, when you just sum them with kind of random kind of alternating sign, it's possible that they are exponentially suppressed. So this non-local order parameter can never provide a reliable criterion to say whether there's something interesting remaining or not. So what we want to really capture is this quantity inside the yellow box. And how can you capture this? In some sense, this is like an information kind of theoretic quantity that captures whether we can still extract long-range entangled state from the noisy short-range entangled state. So let me remind you how we extracted the cat state. So the cat state was obtained by this procedure. You first had this decohered short-range entangled state, where this where the decoherence channel was applied before the measurement, and then you apply this measurement, and then you perform some transformation based on the measurement outcomes. And after doing this, after this very kind of non-trivial manipulation of your decoherent density matrix, you could still show that now this cat state has a very non-trivial correlation structure. So in some sense, all the information is already contained in the decoherent density matrix. So what I do is a mapping of this density matrix into a pure state, because as a condensed matter physicist, playing around with the density matrix is pretty difficult. We are more familiar with the pure state. And the mapping is called a Choi-Jamilski isomorphism, where it's really just a vectorization of this 2 to the n by 2 to the n matrix into the 4 to the n by 1 vector, which is defined in the doubled Hilbert space. So if you have a just density matrix for pure state, then it just maps into a kind of psi conjugate tensoring psi in the bilayer system. And when you have a decoherent density matrix, where now density matrix undergoes some quantum channel epsilon, it's now mapping into a coupled bilayer system. And this mapping is very nice because now the problem reduces into the study of pure state instead of a mixed state, which is an object that's kind of hard to deal with for most of the condensed matter physicists. So let me remind you that the 2D cluster state is this is the SPT state with the two symmetries, the global spin flips on the red qubits and the loop-like symmetries on the white Ancela qubits. And the measurement error translates into having a decoherence on this white Ancela qubits. So once you have this decoherence channel acting on the system, on the ancilla qubits. After Choi-Jamilski isomorphism, this channel maps into this non-unitary transformation. And then what I can show is that still this a coupled bilayer system, this epsilon hat rho 0 is the ground state of a certain local Hermitian parent Hamiltonian, which is parameterized by this probability error rate P. The way it works is the following. Let's say the H0D is the parent Hamiltonian for the original kind of pure state in the double Hilbert space. Then, if you define this H tilde, where A tilde is defined as this, then this H tilde is the parent Hamiltonian for this coupled bilayer system. And in fact, I can show that it's written as the original SPT Hamiltonian plus some coupling between two layers. So at the high level, what's happening is the following. So you initially had a 2D cluster state, but after decoherence, now you get some kind of interaction between two layers. And then you can study basically some quantum phases as a function of this error rate P. And what's really interesting is that in this double Hilbert space, there are two different order parameters you can examine. The first order parameter is some kind of bulk order parameter, which detects whether this quantum states defined in double Hilbert space is trivial or not. And there's another operator defined in the single boundary, whether it detects whether two SPT phases are interlocked or not. And actually, this boundary order detects whether the information can be so this is the kind of conventional order parameter defined in double Hilbert space. And this is nothing physical. You have to map all this behavior back into the original density matrix formalism. And when you do that, what you can show is that this boundary order parameter corresponds to whether information can be efficiently kind of decoded or verified. So this phase actually corresponds to a kind of threshold where you could extract a cat state or a torical state or so on. But now you can ask, okay, what are the other two phases, right? And this scramble phase corresponds to the phase where information is present, but extracting is almost impossible in a sense as the following. So you probably heard that when information is falling into a black hole, it will eventually get evaporated as a form of Hawking radiations. And when things all evaporate into Hawking radiation, in principle, it's possible to collect all the Hawking radiation and recover the original information falling into a black hole. And that was indeed demonstrated by Hayden and Praskill almost like 15 years ago. But what they showed is that this is possible, but just insanely difficult. It will take the time larger than the age of the universe, because the time complexity to achieve this job is exponentially increasing with the entire system. And something similar happens in this red region. The fact that you had this 2D cluster state, non-trivial SPT state is there, but extracting that information requires you to prepare and measure the state exponentially many times. So verifying this information is almost impossible. And I can do this analysis not only for SPT state, but also for long-range entangled state. So I mentioned that long-range entangled state can be used as a robust quantum memory. And the question people often ask is, how much noise can quantum memory tolerate? So for that, what people studied is basically studying certain quantum code, for example, toric code, where the logical qubits are kind of defined as a kind of non-local operator such that it's robust to noises like the dephasing or spin flip. And Kitaev and Praskill have studied that when you encode your logical qubits non-locally in this two-dimensional toric code, errors are correctable as long as kind of error rate is below almost like a 10%. And the way they figure this is they found certain decoder which can decode up to this region. But you can ask the question, I don't want to think about decoder. I mean, in principle, all the information must be there inside this decoherent density matrix, even before talking about decoder. can we capture some intrinsic information theoretic capacity without referring to a decoder? Because as I showed in the decoding phase diagram, whether things can be decoded or not largely depend on what decoder you choose. So how can you capture this intrinsic capacity? We can actually proceed in a very similar fashion. I can perform this Choi isomorphism to a decoher toric code, which you then map into 2 copies of toric code under anyone tunneling. And then I can again construct this information theoretic phase diagram where, so in the double Hilbert space, when there's a tunneling between 2 toric codes, the anions can condense above certain tunneling strengths. So there's 2 copies of toric code will collapse into a single copies of toric code, as you can see in this red region, and then finally to a white region. But as long as you're in this blue region, it means that the logical qubits, the information that you prepare the non-trivial toric code, can be efficiently decoded and verified even. So in this way, you can extract a error threshold, fundamental error threshold of all different types of many-body entangled quantum states without thinking about decoder. This is very nice because coming up with decoder can be also very challenging. And even if you come up with a certain decoder, you don't know how good it can perform. Basically, my framework is suggesting that in this way, you can get the upper bound for how much it can achieve, and then you can try to come up with a decoder that saturates the bound. Sorry for being too hasty, but yeah, okay. So, all right. So the one last remark is that now that our quantum devices are getting better and better, we really want to combine measurements and decoding as a fundamental tool in a sense as the following. When you have a certain entangled quantum state in a device, it will get entangled with the environment. And because of the monogamy of the entanglement, what it means is the quantum correlations within the system kind of shrink because it will develop the quantum correlation with the outer environment. So every once in a while, you want to perform some measurements and decoding to cut things back into your quantum device. And for that, it is really important to understand how measurements can interact with your entangled quantum states so that certain errors can be corrected in an efficient way or not. And this is just one interesting thing I found in a sense that, so it's related to the initial remark that entanglement should be structured enough for measurement and kind of decoding to be useful. Because if your quantum state entanglement structure is too complicated, then like it's almost impossible to process based on the measurement outcomes. I mean, I said that it's important to put things back using measurement and decoding, but when entanglement structure is too complicated, even if you measure some of the syndromes or some part of the system, you can't really learn anything, whether it's entangled with the environment or it underwent any noise or things like that. So in this regard, it's really important to think about what structure of the entanglement, what structure of the entangled state can be properly measured and processed to maintain certain level of quantum information. So with that, this is a summary. So I talked about how measurements and feed-forward operation decoding can give rise to an interesting kind of state preparation protocol. And then I talked about how to understand the fundamental kind of robustness of this using a more general framework where basically we map decohered entangled state into a doubled, in the pure state in the double Hilbert space, and then study a physical phase diagram there, get some understanding, and maps this understanding back into the original physical system. And while doing so, I've showed that there are lots of different phase transitions, and those phase transitions in terms of original physical observable, it's not really a physical phase transition. If you come up with any observable, they just change smoothly as a function of the decoherence strength. What undergoes this phase transition is really a quantum information. And in this sense, my framework of this mapping and talking about phase transition there is really capturing the information theoretic phase transitions of many-body entangled systems. And these are my collaborators. And yeah, thank you.
Excellent. Thank you so much, John.
All right.
Thank
Yeah,
you, Yeon,
sorry for
for the very nice
I
talk.
have a quick question.
sure.
So the question is, right, so you mentioned this this like method for determining the error threshold
Yep.
without without any reference to the decoding scheme, right?
Right.
In terms of like the story code and the threshold for the anion condensation. But how would you like generalize this to a general like error correcting code?
Right. What's nice about this is that, so when I have a dephasing error, it maps to just a ZZ anion tunneling term. But you can also think about all different decoherence model. There can be eraser channel, there can be correlated decoherence channel, and so on. Each of them will map into a different kind of interactions between two layers. And therefore, kind of phase boundary will also change accordingly. And also, you can think about different quantum codes as a topological order, right? So
Yeah.
then you can ask whether interpreting certain quantum order, a quantum code as a topological order. Now, when it undergoes decoherence, it maps into two quantum codes, two topological order under some interactions, right? And you study some phase boundary there in the double Hilbert space. And then you get some understanding, and then maps this understanding back into a physical system.
I see. Okay.
So one understanding is this: when you have a quantum code in like two layers, and then if the interaction is weak enough, then each layer will behave as a proper quantum code, kind of independent quantum code, right? In terms of density matrix language, it's like having a still very non-trivial off-diagonal components that stores logical qubits. But when now tunneling is too strong, when two quantum codes collapse, identified into a single kind of topological order, that corresponds to your density matrix off-diagonal term kind of highly suppressed. So that all the interesting logical qubit information got disappeared.
I see.
Yeah.
So like, so when you talk about this anion condensation, right? So are you talking about the anions on the top layer?
Oh yeah,
and
anion bound
anions on
state.
the
Yeah. So
bottom layer separately, or like are the anions in these two layers like condensing with each other?
So toric code has an E anion and M anion, right? So
Right.
E1, M1, E2, M2. So what's condensing is a E1 times E2.
Okay.
So the composite anion of two layers kind of condense.
Okay.
Yeah.
All right. So you're also mentioning this like boundary order and the bulk order.
Yes.
Could you also like explain it more in this like in this particular context that we just discussed?
Sure. Can you see my screen?
Yeah.
So, okay. So even when bulk order, what it really detects is whether together these two layers of system has some non-trivial quantum phase or not. So it doesn't care whether two layers are identified or not.
Right.
But this boundary order is order parameter at just one boundary. And what it's detecting is whether two layers are kind of independent or not. Because only when two layers are kind of independent, then some quantum information in this entangled many-body states can be efficiently extracted or verified. Because that corresponds to kind of off-diagonal parts of the density matrix being significant so that it can be measured efficiently.
Right.
Yeah.
So
so what's happening is that even if kind of the transition of the kind of independentness of the two layers can be separated from the transition of this entire system being non-trivial to trivial. Yeah.
I see. So does the bulk order, like, since we are like working in the doubled Hilbert space,
Yeah.
right? So are you saying that's like the order that actually survives, if like mapping back to the physical like Hilbert space, is
That's
the
going to
boundary
be
order?
very, very tiny. So yeah. No. What's happening is this. So when you map things back, the bulk, if you want to measure bulk order parameter, that signature will be very, very tiny, exponentially small, in fact.
Right.
And in principle, it can be exponentially small. But boundary order, when you map things back into the bulk, the physical system, it's a finite, so it can be just measured directly.
Okay, yeah, makes sense.
In trivial case, it's just 0. Yeah.
Right.
All right. Yeah. Sorry for too lengthy talk. I mean,
no problem.
Mike said it's going to be informal, and so I was trying to be more thorough and explaining.
Right. No, it was great.
Excellent talk.
I mean, I mean, we interrupted you with a lot of questions, so it's fair that you took somewhat longer. But the presentation was great. I was like able to follow most of it, which is awesome. Yeah.
I mean, the only 2 messages I want to really convey is that really kind of, where is it? Really kind of the box, and then by doing this, and where is it? Right. Sorry. And then this, by mapping into a double Hilbert space, now you can study mixed state densimetry as if they are now a pure state, which undergoes some phase transitions. And when you map things back into original system, that has an information theoretic meaning. So those 2 are main messages I wanted to convey. Which is quite interesting, right? Because this it's like now you have a kind of tool to deal with information using some many-body physics tool.
Right. And they have also like come up with Lieb-Robinson bound for a system like undergoing like measurement plus unitary dynamics, like more recently, which is also like really interesting. If you haven't seen it already, like you'll find it like very interesting, because like these days, like people are considering not just like unitary dynamics, but unitary dynamics combined with measurement. So you can like you can think of you can ask questions like at a certain like measurement rate, like what is the what is the time it takes for the information to go from one end of the system to the other.
But I want to mention that every measurement-based dynamics really reduces into a quantum teleportation. And if you think about quantum teleportation, like when you think about quantum teleportation, the you have to send the kind of measurement outcome information to the other part of the system that's unmeasured. Which means that still things are limited by this classical communication speed. Yeah.
Right.
So I mean, I got to realize that people in this measurement physics community don't really appreciate the quantum teleportation aspect of all this, because like when I think that everything is in some sense just more complicated quantum teleportation, I guess lots of intuitions get more straightforward and simplified. So I think this is all right. Yep.
Yeah, thank you so much.
Well, thank you.
Yep. If you have any questions,